As you look at the relationship between pressure, volume, and temperature for gas behavior, there's one gas law that includes the amount of gas, and that's the ideal gas law. This one's a little bit different than the others because it doesn't compare the behavior of a gas from one set of conditions to another one. This includes N, the number of moles of a gas, and it looks at how the gas is behaving under just one set of conditions. So let's take a look at some of these slides for some more information. Now the formula for the ideal gas law is here. PV equals nRT. P stands for pressure, and you're going to be able to use any of those pressure units that you want. V is your volume in liters. N is the new variable, number of moles. R is a constant. I'll come back to that in just a second. And T is your temperature in Kelvin. So really, nothing there that you haven't seen before. The ideal gas constant is a constant. In other words, it's a number that's always going to be in the equation. It's what makes this formula possible. It makes it an equality. There are three different values for R that you can use, and they're listed in your reference tables. They're here on the right side of the slide. The pressure determines which value of R you use. If your pressure is in kilopascals, you want to use the R value of 8.314, and it's got some other units that go with it. They're going to serve a purpose of canceling out. If your pressure is given in atmospheres, you want to use 0.0821 as your value. And finally, if your pressure is in millimeters of mercury, or torr, you want to use 62.4. So make the value for R and the units for R match the pressure units that you're given in your problem. Now these are going to be word problems, so let me show you what I'm talking about. In this first problem, we've got some methane, and we're trying to figure out how much of it, how many kilograms of methane we have. Let's make a list of what we know. I know that I'm looking for kilograms of methane, and kilograms is going to be related to the moles of methane. So that's my unknown. 225 liters is a volume. 150 kilopascals is a pressure, and my temperature is 35 degrees Celsius. But remember, we don't want to leave it in Celsius, we want to convert to Kelvin. So I need to add 273 to that, and that's going to give me 308 Kelvin. Now the last variable that you need to plug into this equation is that R value. Remember I told you that when your pressure is kilopascals, you want to use 8.314. And it's liters times kilopascals over moles times Kelvin. So let's plug into the equation now, and we're going to solve for N. My pressure is 150 kilopascals. My volume is 225 liters. N is my unknown. Now here's R. This is where all those units are going to go. Liters times kilopascals divided by kelvins and moles. And I've run out of room. I'm going to squeeze in my 308 Kelvin right there. Alright, so when we solve for N, to do our algebra, we need to divide both sides of the equation by 8.314 and 308 Kelvin. And when we do that, a lot of units are going to cancel out here. You know, if I divide one side by these numbers, I've got to divide both sides. So over here, everything cancels out. And what I'm going to be left with is N equals, my kilopascals cancels with kilopascals, liters cancels with liters, and then this Kelvin cancels with this Kelvin. So my answer is going to be in moles. And that's perfect because that can get me to grams. So in my calculator, I'm going to type in 150 times 225, And then I need to divide by 8.314, and I also need to divide by 308. Now that gives me a total of 13 moles. I'm going to do just a little bit of rounding. I'll do 13.2 moles of CH4. Now that's almost the answer, but this question wants to know how many kilograms. So the rest of this problem is just review. We're going to take that 13.2 moles of CH4 and we're going to convert it to kilograms. So I remember that in 1 mole of CH4 there are how many grams? We'll go to the periodic table. There's 1 carbon and 4 hydrogens. That gives me a total of 16 grams of CH4. And then I just have a quick conversion. There are 1,000 grams in 1 kilogram. So that's a really old concept. We did metric units a long time ago. All of these units are going to cancel out. I need to multiply across the top 13.2 times 16, and then I'm going to divide that answer by 1,000, and I get 0.21 kilograms of methane. And that's your final answer for this problem. Let's try another one. In this problem, we're being asked to find the number of grams of carbon dioxide. Let's start again by making a list of what we know. Now I think that 785 torrs is going to be my pressure. Tells me that the volume is 32.5 liters, and it tells me that my temperature is 32 degrees Celsius. But remember to add 273, and that'll give us a Kelvin temperature of 305. You'll always have to work these in kelvins. Now, I'm looking for grams, which is going to be number of moles, and then the R value depends on this pressure unit, torr. Torr and millimeters of mercury are the same thing, so I'm going to plug in 62.4 liters times torr over kelvins times moles. Right, so here we go. Now we're solving for N. So I'm going to plug in. The pressure again is 785 torr. The volume is 32.5 liters. N is my unknown. R from the reference tables with all of those units goes here. And I ran out of room again, so I'm going to squeeze in the 305 Kelvin right here. Now we need to get N on a side by itself. So I'm going to divide both sides by 62.4, and I'm going to also divide both sides by 305 Kelvin because that cancels all of that out on that side for me. So then I'm going to have N equals, units start to cancel now. Torrs with torr, that liter with that liter, and that Kelvin with that Kelvin. So again, we're going to get our answer in terms of moles. You just need to plug everything in your calculator now. 785 times 32.5. I'm going to divide that by 62.4, and I'm also going to divide by 305. That gives me 1.34 moles. So I'm almost there, but this question asks me to find the number of grams of carbon dioxide. So let's just go down here to the bottom and do one last quick conversion. 1.34 moles of carbon dioxide to grams of carbon dioxide is what we're after. Now you need to go to the periodic table and let's add together the mass of 1 carbon plus 2 oxygens, and we get a total of 44 grams per mole. So really straightforward here, 44 times 1.34. And I'm just going to go ahead and round off. You get 59 grams of carbon dioxide in this problem. So you see, the ideal gas law looks a little bit different than the others because you don't have two temperatures or two volumes or pressures. You only have one set of conditions, and you're looking at the amount of gas as well. While we're here, let's take a look at the comparison between real and ideal gases. Now, ideal gases are the ones that follow all these gas laws at all temperatures and pressure. So they conform to all the parts of the kinetic molecular theory that you've studied before. We do assume that ideal gas particles have no volume. They also don't have any attraction or any intermolecular forces between them. And to be honest, gases don't normally behave this way. So an ideal gas is theoretical. They don't really exist. But real gases do exist. We have to factor in the particle volume, or the size of those molecules. We also have to think about the attractive forces, or the IMFs, that are between them. Now, real gases and ideal gases sometimes behave similarly, but they differ most often when you're at really low temperatures or really high pressure. Real gases give us the true picture of gases, but studying the ideal gas law and pretending that gases are ideal give us a simplified picture so that we can predict the behavior of a real gas in a situation. Bring your questions with you and have a great afternoon.